Hey, welcome back to Advanced Mechanics. We'll be looking at our next example using the Lagrangian, which is the simple pendulum, and we're going to do it in two different methods. So here's going to be the first method using polar coordinates. In the next example, we'll use rotational kinetic energy. So let's start it off. We have a pendulum here with a massless string, and it's going to bob back and forth. So what are some things that we want to know? Well, we can break it up into its components, L, which is going to be L cosine theta and L sine theta. We know that this mass is going to have some velocity tangential to the string, so it could either be going this way or going down that way, which means it's going to have an x component and a y component to the velocity. Along with the x and y component of the velocity, it's going to have an x and y component for position. So what we're going to do is we're going to write down our position vectors, or our position values first, and that's going to be given by x is given by this value right here, which will be L sine theta, and y is going to be given by L minus L cosine theta. So y is this distance right here, x is the distance from here to here. Now, why is y L minus L cosine theta? Because the entire string, when it's down here, is going to be a length L, and you have to subtract this distance from it to get the delta y, or the y value. So those are our generalized x and y coordinates. Along with the generalized x and y coordinates, we have the generalized x and y positions as well. How are we going to write that? We can write that as Vx, which will be the component of the velocity going this way. So that's Vx. The angle right here, theta, is going to be the same over here, so this will be cosine theta. So we would write this as Vx is equal to dx over dt, but we know what x is equal to already. X is equal to this, so if we take the derivative of L sine theta, it's going to equal L theta dot cosine theta. Because this is implicitly done, you have to take it with respect to time. It becomes cosine, but you also need to multiply it by the derivative of the inside, which is theta. How about y? Vy is going to be dy over dt, and that's simply going to equal, well, this term is a constant that goes away, and the derivative of cosine is negative sine, so a negative negative becomes positive, but you also need to include that theta dot term, just like in this last one. So we end up with L theta dot sine of theta. So now that we have our velocities, we can write down our kinetic energy. The kinetic energy, Ke, is equal to 1/2 the mass times the velocity in the x direction squared plus the velocity in the y direction squared. So you have kinetic energy in the x and kinetic energy in the y. And we can rewrite that as 1/2 m parentheses all of this thing squared. So that's going to be L squared theta dot squared, cosine squared theta, plus L squared theta dot squared sine squared theta. From here, it looks like we could factor out the L squared theta dot, and we end up with 1/2 L squared theta dot squared, and on the inside we would be left with cosine squared theta plus sine squared theta. You should know that this is a identity. Cosine plus sine is 1, so we just end up with 1/2 L squared theta dot squared. That is our kinetic energy. That was pretty clean, wasn't it? So, oh, and I forgot the m. This is why it's important to always check your work. So we get 1/2 m times L squared theta dot squared. That is the kinetic energy. What about the potential energy? The potential energy, PE, is equal to, let's see here. So if this is our starting height, mass is up here. What is y? Y was equal to this right here. So it's going to be mg times y, which is L minus L cosine theta. Potential energy will be mg L parentheses 1 minus cosine of theta. Now that we have the kinetic energy and the potential energy, I'm going to take this term and subtract it from this term right here, because that's going to give us a Lagrangian. So the Lagrangian, I'll write it right here. L is equal to the kinetic energy minus the potential energy, which is going to be 1/2 m L squared theta dot squared. Now, I have to put a minus sign here. I have to put a minus sign front. So what I'm going to do is I'm just going to flip these two right here and call it an addition sign. So it'll be plus mgl cosine theta minus 1, just to make my life easier. To make it even more easier, I guess I could distribute the mgl into here just for when we take the partial derivatives. So we'll just say that L is equal to 1/2 mL squared theta dot squared plus mgl cosine theta minus mgl. All right, so now that we have the Lagrangian, we can use our Euler-Lagrange equation, which is simply d dt, the partial of the Lagrangian with respect to velocity. Oh, and in this case, our velocity is the angular velocity, theta dot. So I'm going to write it as theta dot minus the Lagrange, or I guess the partial of the Lagrangian with respect to theta is equal to 0, where theta dot and theta, are our generalized coordinates instead of x and y, since we converted it. All right, so we need to find both of these values here. Which one should we start with first? Let's do this term because we don't have to do two different derivatives. So dl over d theta is equal to, so looking over here, there's no theta term here, that's a constant, gone. There's no theta term here, that's a gone. There's a theta term here. The derivative of cosine is negative sine, so we end up with negative mgl sine theta. Okay, so we've solved for this term, which we'll plug in later. What about the dl over d theta dot? That's going to equal, well, this term right here, the 2 goes into the front here, and it'll become ml squared theta dot, and then we have to take the time derivative of all of this. So d dt of ml squared theta dot is going to equal, you just take the derivative of that with respect to time, and that's going to be ml squared theta double dot. So we have our two terms. Here is here, and this is that. So just do the quick substitution, and we're good to go. So we'll have ml squared theta double dot minus negative mgl sine theta, and all of that is equal to 0. The m's will cancel out. What else can we do? We can divide everything by L squared, and we will end up with theta double dot plus G over L sine theta is equal to 0. So that's what we have. And then what we're going to do with regular mechanics is we always take a small angle approximation. So with a small angle, we can say that sine theta is roughly theta, and our differential equation will become theta double dot plus g over L theta is equal to 0. And from this, we could say that g over L is equal to omega squared. So our differential equation becomes theta dot plus omega squared theta is equal to 0. And the solution to this differential equation for theta as a function of time is going to be, again, we're going to start just like with the spring at some amplitude. So it'll be cosine instead of sine, but you could put sine there, it doesn't matter. It just depends on what the starting point is. So we get theta dot is equal to theta max cosine of omega t. And that's our solution. But really what was important was this right here. And we got this from using the Lagrangian and the Euler-Lagrange equation. So that is the value we got using this method. Now we're going to do the same Euler-Lagrange technique, but we're going to apply a slightly different technique to solving for it. So here we're going to look at a same example, and we're going to do it a different way. For method 2, what we're going to do is we're going to write down the rotational energy, because this thing is rotating about this central axis. You could think of this as like a point that's fixed, and this object is rotating back and forth from it. So there's going to be an angular component to it, a rotational kinetic energy. And when we write down the Lagrangian, which is T minus V, what is T going to equal? T is going to equal 1/2 I omega squared. I is going to equal m L squared, because L you could think of sort of as the radius about this axis point right here. And omega is going to equal the change in angular position over time, which is just theta dot. So we can do the substitution for the kinetic energy, and the kinetic energy is going to equal 1/2 parentheses ml squared times theta dot. That's our kinetic energy. The potential energy is exactly the same as we did in the last example, because this is our starting point. So the potential energy is going to be mgl 1 minus cosine theta. So this is already a lot easier than the last one. These are our two different types of energies, and that's it. This just has a rotational kinetic energy. From here, we can put it into our Lagrangian. The Lagrangian simply states that L is equal to the kinetic minus the potential, and that's just going to be 1/2 ml squared theta dot minus this term right here. So we'll just flip the signs here. It'll be minus or plus mgl cosine theta minus mgl. So there's the Lagrangian, and now we put it into the Euler-Lagrange equation. We first need to figure out what dl over d theta is equal to. This term is nothing. This term becomes negative mgl sine theta. For the other term, we have dl over d theta dot, and that's going to equal ml squared theta dot. From here, we could actually probably put it all here. dl d over dt of dl over d theta dot will equal ml squared theta double dot. It's exactly the same value, right? We plug this term in, we plug this term in to the Lagrangian, the Euler-Lagrange setup. we will end up with, I'll write it up here, ml squared theta double dot minus the negative of this, which is plus mgl sine theta equals 0. The m's cancel out. You divide both sides by this, but also sine theta is equal to, roughly equal to theta for small angles. And we end up with theta double dot plus g over L theta is equal to 0. So we end up with the same result, just in a fewer steps. And that's the Lagrangian technique for the simple pendulum. I'll see you in the next lesson. Adios.